Welcome back. We're now going to look at our last chapter in mechanics, and we're going to be looking at, in this chapter, circular motion and then gravitation and how they combine together. So the title of this chapter is actually rotational motion, the law of gravity. We're actually going to change that. Instead of rotational, we're going to look at it more of circular. Hang on, I got to spell it right. Circular motion. The only reason I make this difference is because later on, for those of you that are going to eventually go on and take AP, we're going to have another topic called rotational, where it's very similar, but we're going to look at it from a different standpoint, and we're defining a whole bunch of other stuff in terms of like radians instead of meters and stuff like that. So we're going to look at more of a simplistic view of circular motion rather than rotational. So in circular motion, there are many examples of this. You could talk about a merry-go-round or a Ferris wheel, or being in orbit around the Earth would be an example of it. Even if you're just taking the keys and you're swinging around your finger. Those are examples of circular motion. Now, we need to define something because, again, our whole point is being able to describe this motion. And so we're going to start off. So if this is my motion and an object's going around, we'll have it going around, clockwise at the time being. So if it goes around here, first off, we have to define the time. The time it takes for him to go to some start, to go all the way around and finish in the same spot. The time it takes to do that is actually a special time that's called period. And that period comes with its own symbol, a capital letter T. It is still time. It is still measured in seconds. But it is the time it takes for it to go around that circular motion one time. And so if we know that, we're now going to be able to find the speed of that object, because remember, speed is just the distance divided by the time. Well, if you're going to go around a circular object once, that distance actually has its own special name called circumference. We'll divide it by the period. Now, the circumference, you don't have to remember how to find the circumference of a circle because it gives it to you in your reference tables. It is equal to 2 pi times the radius, and then we'll divide that by the period. And this will give us the speed at which it goes around. Now, please notice that this is just going to be the speed. This is not the velocity. The velocity, on the other hand, is going to be constantly changing because the direction is going to be changing. So if I go back, we're going to have this thing moving in a circular path. Okay, and let's say, again, it's moving in a clockwise pattern. Well, if I'm at the top, it's going to be traveling in this direction. And when you come into class tomorrow, I'll demonstrate this. So this will be the direction of its velocity. When it's here, its velocity is now down. When it's here, it's traveling over. When it's here, its velocity is traveling here. This velocity is always tangent. Put the end in there. To the circle, or to the circular path. Okay? And so by tangent, you should remember this from math, but it intersects the circle in one point. Okay? But in order to get this velocity to change, if I'm here, actually, I'll put this in purple. If my velocity is traveling to the right when it's at the top and I want it to go down, I'm going to have to cause an acceleration down. That's going to be my change of velocity. And I will go into this a little bit more detail tomorrow and show you how that occurs. But if I'm over here and I want to be traveling to the left, I'm going to have to accelerate to the left. If I'm going to the left and I want to go up, I'm going to have to accelerate up. If I'm going up and I'm trying to go to the right, I have to accelerate to the right. And so my acceleration is going to be always towards the center. This acceleration is directed toward the center. Of the circle. run out of room. There we go. Okay. So since there's always this change velocity, there's always that acceleration. Okay, we can find this acceleration. Well, you've got the diagram. We can find that acceleration, and this is a formula that I will give you. And when we go into AP, if you go to AP, I'll show you this, and I may touch on it tomorrow in class. But it's not really anything crucial you have to know. But in order to find that acceleration, it's equal to the speed squared divided by the radius. Okay, and I put a little a sub c there to tell you that this is a special acceleration called the centripetal acceleration. And centripetal literally means center seeking, because that acceleration, if we go back up and take a look, that acceleration is always directed towards the center. It's center seeking. Okay, and so it comes with its own special name, centripetal acceleration. Real quick, you can also find, if you want to know the centripetal acceleration in terms of the period, we can use that same equation, v over r, v squared over r. But remember that the v from before is 2 pi r over the period. Therefore, v squared would be 4 pi squared r squared over the period squared. And so if I take and I substitute in this v squared with that v squared, I would get 4 pi squared r over the period squared. Now, a lot of people say, wait, it was r squared down here. How come it's not squared r squared up there? The r squared gets canceled out with the original r that was in our equation. So this is an equation that is not in your reference table. You are welcome to put it in if you want. But again, you can very easily, use our speed equation we derived before to determine what the speed is, and then plop it into our centripetal acceleration, which you do have. Now, recall that anytime there's an acceleration, that means that there is a force. And so anytime that I'm moving in my circular path, I have to have a centripetal force also directed towards the center. I'm going to label this F sub c to let me know that that is a special force called the centripetal. It is always directed because the force, and actually let me rewrite that, the net force is in the same direction as acceleration. And I can now write out my centripetal force formula because it's just Newton's law. Because if I'm talking about F equals ma, if I now want to talk about centripetal force, I'm just going to use the centripetal acceleration. And so F sub c is equal to m times a sub c, or mv squared over r, or m times 4 pi squared r all over the period squared. Get rid of that sp part. Okay? So a bunch of different ways. And again, these are not all listed on your reference table, but you can derive them relatively easily. Now, the last thing we're going to talk about today is called centripetal versus centrifugal. Okay? And we'll get into a little bit more detail on this. But remember, centripetal means center seeking. Centrifugal is actually a fake force. And let me give you an example on this. If you are riding along in a car, okay, you can envision this, you've all done this. And all of a sudden, somebody in that car turns relatively quickly to the right. And so if you imagine, oh, it turns to the right, you actually feel as though you're being pushed to the left. It feels like there is a force that is pushing you to the outside of the curve. If you've ever been on, I forget what it used to be called the UFO as the thing, but it would be this thing where you'd stand up in the amusement park ride and it would start to spin. And then it would spin and it would make you go vertical. And so you'd be pinned to the wall. You'd feel as though there was a force pushing you to the outside. Now, that's not actually really a force. It is your inertia. Because, and again, if I just draw a real quick picture of a car here, And I'm going to do a really poor job, but you get the idea. There's my car. There's its wheels. So if this is you, okay, and there's somebody else, I kind of looks like I'm in a SpongeBob, but I apologize. Again, drawing not a good thing. But let's say I'm turning to the right like this. Your inertia, and I'll put this in blue, your inertia wants you to keep going straight. I can't, there we go. Keep going straight. And so it's your inertia which actually makes you want to go straight. It's the centripetal force, which I'll put here. Says this, your centripetal force is actually causing you to turn in. If that centripetal force would suddenly disappear, you would continue going straight. And there's always talk about, they always have these, well, not always, but they have accidents on roller coasters and stuff like that where something fails. And the last one I can always use as an example, at Darien Lake, there was a Superman, and a guy got on there and was not properly strapped in. And when it went over that first big hill, because he wasn't strapped in, he didn't get centripetally accelerated to go with the car, and as such, he got ejected out. And so it's his inertia kept him going straight, whereas the car turned. And if you don't have that force acting on you, then you continue to go straight. And so that's what the centrifugal force is. It's actually a fake force. So centrifugal means fake. We'll discuss this more tomorrow as well. So this is a good place to end. We'll talk about gravity tomorrow. So everybody have a fantastic evening. Talk to you later. Bye.